Thanks, Johannes. Thank you for inviting me to give this talk. I hope you don't regret it too much. So I wanted to talk about what is an exoflop. This kind of, I didn't think about this when I was deciding to give this talk because I like these objects, but I find that they kind of come with like the baggage that they keep everyone unsatisfied. It's not quite a flop, so the birational geometers won't like it. It's very derived in a lot of ways, so the toric geometers don't like it as much, and then it's usually in toric, so then the derived geometers don't like it too much. And then it's becoming, we're apportioning it into algebraic geometry, so then the physicists don't like it as much as when they originally did it. So I'm hoping that you all can go with me and like not feel too dissatisfied when you see what an exoflop is, because it kind of has all four of these things building together. Okay, so what I'm going to start with is some type of toric preliminaries so that we all have the same notation. And then I'm going to explain through an example of what an exoflop is, which is very related to a Landau-Ginzburg model. And then I'll explain a few examples of why this thing's useful. Okay, so let's start. And please shout at me if you can't see anything on the screen, and if I need to write bigger or if I'm going off the page. I think we've tried to make this work, but you know, I might move the sheets of pages and then it might go off. Okay. All right, so let's start with section 0, which will be toric preliminaries. So as first, I'm going to start over C. What I'm saying mostly works over any algebraically closed field of characteristic 0, but I'm just going to go over C today. All right, so as any toric geometer, I'm going to start with let M and N be dual lattices. And then I'm going to take sigma to be a complete fan in NR. And I'm going to assume that the toric variety associated to it is projective. Okay, so what we have when we do this is we have a short exact sequence that gives us the class group. So we have the short exact sequence. Um, 0 to M to the just a free abelian group ordered by the rays in sigma to the class group of X sigma 0. Okay, so then what we can take is some torus Weil divisor D in the class group. And it can be written in the following way. As D equals the sum with some coefficients A rho, D rho, where rho are rays in the fan. So as a torus Weil divisor. Okay. And then we can make the fan for the total space tot OX sigma of D. Okay. This is a fairly straightforward kind of construction. This is done in section 7 of Cox-Little-Schenck. And how does it go? Well, first I'm going to make sure when I move this page over, I'm going to get the right number. Okay. All right. So this is page 1, page 2. Okay. So so we do this in the following way. Okay, so first we extend the lattices to n cross z and m cross z. And then given any cone, sigma inside sigma, set sigma twiddle to be the cone over, we just have this 0, 1. This is just going upward out of a page of m and n, right? Or of n. And then we take u rho minus a rho, where u rho is the minimal generator, minimal lattice generator. For rho in sigma 1. And we do this for any rho that's in the rays that are inside sigma. Okay. So then we can construct a fan with all these cones, sigma twiddles. So we'll call it take sigma sub d to be the face, or to be the fan of proper faces, or no, maybe of faces. I don't need proper faces. No, I don't. Of all sigma twiddle. Okay. And then the proposition that we end up with, this is 7.3.1 of Coxwell-Schenck, is that the toric variety associated to this new fan is the total space of O x sigma d. Okay. So now let's do this in an example. Okay. So an example of this. Well, let's look at P2 because that's our lives, right? I mean, we always start with P2 with this, right? So P2 has a fan that looks like this. And then I'm going to take the divisor to be minus 3h. So minus 3 times the hyperplane class. So I can rewrite that as just minus d rho 1 minus d rho 2 minus d rho 3. And what we end up with is some cone in 3 dimensions where these outward things are, if this is generated by -1, -1, this is generated by 1, 0, this is generated by 0, 1, and then this is -1, -1, 1, because we use the divisor to grab the slope that we're going to go up on in order to make this. Okay, so we end up with 1, 0, 1, and then 0, 1, 1 in the back here. But then we also have this piece in the middle, this 0, 0, 1, and we're kind of star subdividing here. Okay, this gives us the total space of O of minus 3 in P2. Okay, any questions so far? All right. So that's one proposition from one textbook. Let me give you another proposition from another textbook, okay? So how do I? Oh yeah, and it's really nice to see so many friendly faces. Thank you so much for coming. All right, so what I can then do is some type of Cayley trick. Okay. So if I have, this is like outside of the toric setting. If I have some variety, say dot y, this is some quasi-projective variety. Okay, and then I suppose I have a section say S in here and Y that is a global section of some vector bundle E. Then I can make a function from this. So this is some exercise in Hartshorne that we all claim as algebraic geometers to have done, but that's not true. You know, let's break the myth that we've done every problem in Hartshorne, right? So unless you did, and bravo to you, right? So the function we end up with a global function on total space of E dual in the following way. Okay, so what I have is I have this section over Y. Okay, and then what I can do is I can pair that thing with the fiber. The fiber in the dual to get a function, right? So this is just pairing with the section. Okay. But we can write this in coordinates for the last example. So doing this in the following example, the following. Okay. So we take some cubic f in P2, right? So then f is inside gamma of P2 O of 3. So that's going to make a global function on the total space of O of -3 to C, given by pairing. Okay. But there's a better way to write this. We can write this as UF, where U is this bundle coordinate. Okay. And the way we see that is we can see it on the fan, right? We can think of, this is X and this is Y and this is Z, but then we have this bundle coordinate that's coming from 0, 0, 1, right? And we have that this dual cone, or that this cone has global functions that are given by looking at the dual cone. The dual cone gives you all the global functions on this toric variety. So in particular, we can see a correspondence between the lattice points here in the dual cone to this one, and the ones that can be thrown into here as a global function. Okay. So that's the Cayley trick. Okay. In case you don't remember it. Or never did it. Who knows? Okay. So right. So I want to explain now what a GLSM is, because in the abstract I very clearly explained what an exoflop was, right? All right. I have no idea why it's called the Cayley trick. This is something that's been passed down to me by being called the Cayley trick for so long. So that's a good question, and I never questioned it, so I don't know. Okay. So an exoflop I don't know. Occurs in the gauged linear sigma model. By varying the Kahler form so that a subspace appears to shrink to a point and then reemerge outside the original manifold. Okay, so that's the definition that definition, right? That's a joke, right? This is what Aspinwall said in 2014. Okay. And I want to kind of unpack this definition in this talk and explain how it's kind of shown up in my work. And but first, I kind of need to bring this to kind of an algebra geometric language to some sense. So first off, not all of us work with gauge linear sigma models all the time in our lives. So we should kind of just unparse what that means. What is a GLSM? So it is something that we see a lot, but we just don't see the language of it. So it's a suite of data where you have X being a quasi-affine variety. You have G, which is a linear reductive group, linearly reductive group acting on X. And then we have some character of G. And then we lastly have W, which is some G invariant regular function from X to C. So in particular, we can think of this as we have X, and then we can take the GIT quotient by G using the character chi. And then we have a function that is now living on this GIT quotient. So it gives us some Landau-Ginzburg model. Okay. So let's kind of explain what happens in our example here. Okay. So let me maybe move this up here and write this. So the example that we have there, okay, is that if we have X to be kind of C4, and I can either take the locus that's going to be taken out by the unstable locus with respect to chi earlier or before, right? So I'm just going to take it out now, and I'm just going to take out Z, the zero locus of X, Y, and Z. So I'm just taking that origin away from the P2. And then I end up with some G, which is some 2 copies of C star. So this one acts just the way that the GIT quotient that gives me this total space does. It acts by weights 1, 1, 1, minus 3. And then this thing is something called R charge that I'm not going to get into. This kind of just goes along for the ride, and we're going to just be happy with that today because it's a pandemic. Struggle is real. Okay, so and then we have UW being UF. And you can see that this is invariant with this, and it just has to be semi-invariant for this one. Okay, don't worry about the R charge. I think that's something that Ed will agree with me is to don't worry about the R charge right now. Okay, so so this kind of matches what we have here. So it's a way to think of it is this global function. Okay. All right. So that's what a GLSM is. Now, why would we ever look at GLSMs? Well, it's a more malleable way for you to encapsulate what you might want to know about your variety using a singularity theory. Okay. So there's this beautiful comparison theorem in derived categories that you can use to pass all your derived categories of complete intersections into matrix factorizations. So a categorical comparison theorem is the following.
Tyler,
yeah.
Can I make a quick comment? Hi. I don't think you're allowed to call it a GLSM, like a linear. The L is for linear, so I don't think you're allowed to call it that unless X is a vector space. Hello?
No, I'm listening to you. Sorry, you can't see me. I'm looking off into space while I'm thinking about
Okay.
that. Yeah, I think I'm like abusing a lot of notation, right? So, I mean, what I should be calling this is a gauged LG model, right?
Sure. Yeah.
Yeah. So maybe I'll just, well, that's going to be true for everything that I do in this talk anyway. So yeah, let's just make this some AN. So or CN, right? Yeah, I think you're right. Yeah, this has to be an so this is just an affine variety, affine space. Okay, are we in agreement now?
Yeah, I'm fine with that. Thanks.
Okay, cool. Okay. So yeah, maybe I'm worse than the physicists in abusing definitions. Yeah, we should not give them much about that. We should just give me all of the crap about that. I'm not going to say what I want to say because I'm being recorded. Okay, so what we have is if we look at the zero set of okay, what do I want? Yeah, okay, let's look at the Kahler trick again, right? So if I take the zero set of this S, this will correspond to looking here. So I can actually show that this is the same as the category of equivariant matrix factorizations of the total space of E dual when we look at this pairing. Oh wait, this is the wrong slide. That's not what I want. No. All of my notes are, I corrected this somewhere. What do I want? Oh yeah, so, but I want this to be equivariant with the R charge still. So this C star continues, this R charge. Yeah. But in reality, what this really thing is that I rewrite this thing as an actual GLSM by thinking of it as the matrix factorizations on, I rewrite this as a quotient. So this becomes something that's like, so maybe I should just say what's really happening. So really, I think of the total space of E dual as U mod G, and then I end up with matrix factorizations where this is U comma G cross the R charge with the pairing. Okay. And this is an equivalence of categories, and this is given by, and when G is trivial, then you end up with, this is what Isik and Shipman proved, but and then you also have this equivariant version by Hirano. These should be commas, I guess. All right. So let's kind of talk about why this works. So essentially, matrix factorizations tell you the singularity theory. So what is the critical locus for this pairing? So if I look at it in this example of UF, it looks like the following. So I have the zero locus of this thing is exactly the zero section when U is equal to 0. But then it's when F is equal to 0, but U can be whatever it wants to be, right? So what happens is these intersect in some point where U is equal to F, right? So we end up with this kind of piece here that is exactly where F vanishes and U vanishes. So it looks exactly like the zero locus of the function F. Okay. And that's the singular locus. Okay. So in particular, you have that the zero locus of S is smooth. Oh, wait, maybe I should say F. I'm mixing F and S. Let's just say F is equal to S. Okay, and I'm doing this in like rank 1. Okay, so what this is equivalent to is if the critical locus of the pairing UF was proper. You know, if it weren't smooth, then I would have some critical point. Maybe I'll do this in blue, but then that would be critical no matter what U was. And then I'd have a C worth of this and it wouldn't be proper, right? So what I need is I need to make sure that the critical locus of whatever my global function is proper. So that's exactly what an exoflop does. So what an exoflop does is I'm going to just consider our example again. Can you see this? Do I need to move it over?
We can see that.
Okay, great. So consider our example. If I have some toric, you know, this total space of O of -3, then I can, if I have some function that's not going, whose critical locus is not proper, I can try to make it proper by taking a partial compactification. So try to make proper. With a partial compactification. Okay. Now this looks kind of weird because, you know, it was a total space and now it's not a total space, but this relates to a different total space. So if I take some type of toric flop, then I end up with this kind of variety. So I get this fan. And then this is the total space of the canonical bundle on the blow up at a point in P2. Right, because the fan underneath this this is just if I blew up at this point corresponding to this maximal cone. Right? So in essence, what we've done is changed partially compactified, but on the downstairs, it's something that's in the GIT fan of a of the blow up. Okay. Any questions? So one thing that this does that that is not ideal is that it has a side effect, which is the dual cone ends up being smaller. So we cannot use the full linear system of the original vector bundle, okay, or line bundle. You can do this iteratively and look at this. You can use Cox-Littleshank 7.3.1 iteratively and then get a vector bundle and do the same thing for the vector bundle. But I just wanted to talk about this one line bundle case, okay? So you can use this to analyze some singular special linear system inside the linear system of some toric divisor. Okay. So I hope that's made sense on what the exoflop is. So let's kind of review the definition and to see how much of this makes sense now. Okay, so this was the definition. An exoflop occurs in the gauge linear sigma model. So that's because we're dealing with the fact that we're on some Landau-Ginzburg model or some GLSM that's given through this comparison theorem. And then the varying the Kahler form. So what that means is that you're changing the choice of maximal cone in the secondary fan. So this is some variation of GIT, of toric GIT, so that a subspace appears to shrink to a point and reemerge outside the original manifold. So this outside really means this partial compactification. And then the shrink to a point and reemerge outside really means this toric flop through the secondary fan choice of cone. Is everyone happy? I wish I could get feedback of people nodding their heads. Like, can I get emojis in the chat? Does that work? I'm not asking you to turn on your video. I see how that worked with Dan. I'm sorry. No? I'm getting one thumbs up, but I feel like it's biased because it's from the organizer and my PhD student. Okay. Everyone else has already left and they're not watching.
I think the chat is unavailable to people who aren't members.
Oh, okay. Thank you for interrupting that. Okay.
Yeah.
Thanks. All right.
I'm still watching. Okay,
good. You can tell me when I'm wrong the next time. Okay, so what this harks back to is so Aspinwall also says that these things are useful for non-commutative resolutions. Okay, so let's talk about those. Okay, so let me kind of explain what we expect for a resolution in the context of the derived category. Okay, so if I let Y be a singular algebraic variety, then I can take pi being just the resolution of singularities with Y twiddle. Okay, so then we get two functors. Push down, the derived push forward from dB Y twiddle to dB Y. And then we get the pullback dB Y to dB Y twiddle. Okay. But, oh, sorry, this should not be this. This should be perf. Okay, so this is where d perf is the is perfect complexes. Okay, so those are complexes of sheaves that are locally quasi-isomorphic to a bounded complex of locally free sheaves of finite type. So basically, locally, you end up getting some complex of vector bundles. So, you know, when you're smooth, the derived category is just the category of perfect complexes. Okay. So what we have now is that the derived pullback is left adjoint to the derived push forward. Now, moreover, if pi is crepant, then the derived pullback is isomorphic to the right adjoint of the right adjoint to, yeah, pi, the derived push forward. Okay. So what a categorical resolution does is it emulates what these things are. Okay, so we want, instead of finding this resolution of singularities, what we find is some replacement category that goes in these places. Okay, so the definition, according to Kuznetsov, is a crepant categorical resolution, or a CCR, is a category that replaces a category, say, D twiddle, and functors that serve in the same way. So star and double star. Okay. And the main thing that I want to say is that good exoflops give CCRs. Right? So that's great. So that's what I want to outline right now. So let me find where in this mess of papers that is my desk, the next slide is. Okay, cool. So how do I do this? So if let's talk about the setup. If y is a
Tyler?
Yeah.
The notes are just a little bit off the page on the left. So if you can just a little bit further.
I can only imagine what my notes that were recorded 4 weeks ago for my students look like now.
Yeah, this is good. Now I can read it all. Okay.
Oh, this is fun. Okay, so maybe I should use X now. So suppose I have X, which is a smooth quasi-projective with a G action. And I have some S, a regular section of that is G equivariant of a G equivariant vector bundle, say E. And then I have with Z just being the zero set of S. And then I take this R charge that's just the GM that acts by fiber-wise dilation. Okay. Then if I suppose further, so this is the setup for the theorem that Favero and I proved in like 2016, is suppose X admits a G ample line bundle. Okay. That's just some technical thing, right? So let U be a G cross GM equivariant, or yeah, equivariant partial compactification of the total space of the vector bundle. Now assume your section or what do I want? Your global function given by pairing that I'm going to define as this fiberwise, or this pairing, extends to U as a section I want to say here. Oh, do I need this? This is what I need to say. So so I need an extra condition here. So W, this W, when I look at this pairing, it needs to be a section of the total space, some vector bundle, right? So, or some line bundle, right? So it's just I have some character chi that gives me a line bundle, and then it's like this, okay, as a section of chi. And then I have some niceness properties about some finite diagonal, but most importantly, I need that the critical locus, when looked at as a quotient of G, so this is the critical locus of on U, viewed as some subset of G, is proper over K or over C. Then this matrix factorization category is a CCR of the original zero set when I look at it quotiented by G, okay? So what you need to do is you just need to satisfy all these properties, and then you have a CCR, okay? But you can do all of these things just kind of torically. So we give you kind of the tools in this paper how to do it torically. Okay, so I'm lying just a little bit because our definition of CCR is a little different with a little different context than what Kuznetsov writes, but you can also read the remarks in the paper but that's getting kind of in the middle of the weeds. All right, so let me give you an example of why this is actually useful. Okay, so an example is cubic fourfolds. So can you still see if I move it this way a little bit?
Yeah, that's good.
Okay, thanks. All right, so an example is singular cubic fourfolds. Okay, so let's see what this does. So take f to just be the following function. So x1, f2. I'm just going to take some quadric in the variables x2 through x6. And then I'm going to take some cubic in those last 5 variables to x6. Okay, so that's just where this is some quadric. This is some cubic. Now, and ZF is contained inside P5. Okay. So the singular locus of this thing is just at 1, 0, 0, 0, 0, 0, 0. Okay. But we still have Orlov's theorem that the dB co of Z of F by Orlov is that this is some semi-orthogonal decomposition that looks like this. And if you follow this story, you know that for a cubic fourfold, for a smooth cubic fourfold, this is some K3 category, and the conjecture of Kuznetsov is that the cubic fourfold is rational if and only if this is a geometric category, meaning this is the derived category of coherent sheaves of some K3 surface, right? But let's look at this example. Okay, so I want to smooth this, but not quite smooth it. So what I can do is I can take X to be the blow up at a point P5, namely this point, right? I'll call this point. Then I can make some new function f that's going to be given by taking the global functions on this L, where this L is the L, so that when I change this function to be like, I'm going to have some new thing, new y here in order to make a global function on this blow up, right? So this is just yeah. So maybe I should just write this down. I'm being really lazy. I'm sorry. I mean, you could compute this L by just looking at the just taking the blow up and just taking the right level in the toric variety, or you can just write down where this global function is, and there's many ways you could do this. I just didn't have enough time before I gave this talk. Pandemic is really getting to me. Okay, so or the semester. I don't know what's getting to me anymore. Trump. Okay, so torically, when we look at the if we look at the total space of L duo, what we get is some GIT fan. And what it looks like is it's two-dimensional. It looks like this. Okay. And we have some minus k here. That's where the canonical bundle ends up. And the way it works is that as you go from chamber to chamber in the GIT fan, you get fully faithful functors of the matrix factorizations that are going between them. And this is what physicists call flowing to the infrared. I don't know what that means at all, but I have gotten an email saying that that is what it means. So so let's kind of fill out the picture of this GIT and say what each of these things look like. So this one, where the minus k is, it's the total space of L dual with the function f. So what this corresponds to, when I compare, I can use Isik and Hirano to get the dB co of the blow up of the singular cubic, where Z sing is ZF. Okay, ZF twiddle. Well, yeah, it's okay. Now this course compacted the total space of my original cubic. So I CR, and then 2 4 given by a cubic and a quadric. So I end up with when I use Exo-Flop and horizon by a cubical functor going between them. Um, this is a CCR of A. So I find something that is a categorical resolution of this original interesting piece, this Kuznetsov component. Okay. Any questions about this example? The upshot is that categorical resolution and using this as a derived category for me. Okay. So maybe I should say more about this in symmetry. So have I run out of paper? No, I don't. So in I'm not going to rewrite this. So see, so one thing that's important is this is kind of extremal transition. Is you can deal with, or you can smooth out. So the smoothing is when you actually go to the more general version. So in here you have some type of singular fourfold, and then you can smooth out to a generic cubic fourfold that's going to be smooth. Or you just blow up and then you end up, okay, so this is it. And another is categorical resolution. You can use the following theorem of Orlov. So Orlov says that if you have some G equivariant open immersion, so that the critical locus of your function is contained in the smaller one, then their matrix factorizations are equivalent. Okay. And this is really useful. So especially in the field of constructing mirrors. So there's been a lot of mirror constructions in the literature, and often they don't agree with each other, particularly like Berglund-Hoops mirror symmetry. Sorry. Is it that my it's probably my internet. Is everything okay now?
Yeah, there was some cut-offs, but I think it's now okay again.
Okay.
Sorry.
So what we can do is we can I don't know what's on this page. So what else do I want to say? So here's another example of something that's like this. Yeah, let's just show this, and then we can figure this out together. Okay, so what we can do is like I have this example of this kind of global function that is that I'm just looking at P2 mod Z3, and then I take the total space of that. But then I'm going to put in this extra ray here. So I have one at -1, 2, and then I have, this is 0, 0, 1, and then this is 2 -1. And this is all at height 1, right? And this is like -1, 1, 1, and this is -1, -1, 1. And yeah, so this is the superpotential that I can write on this just by looking at the dual cone to this thing, right? And I can make two different ways to look at this. So I can look at it as this when I contract this one piece, so then I get some section of the total space of cubics on this that are invariant. And then that's when I get rid of this y1 prime that's associated to this rho 1 prime. Or I can just take it as a partial compactification of this smaller thing. And that would be if I took the y1 and set it to 1. Okay, so this is essentially what we had as a Kreutzer-Skarka cleave from last week. Okay, so then what you can do is you can compare two derived categories of different hypersurfaces and different weighted projective spaces, or fake weighted projective spaces, by going up to the matrix factorization category and then doing some VGIT and exoflop magic in conjunction with this Orlov theorem. And and then you can go back down. And this is the technique that we've been able to do in order to prove the equivalence of mirror constructions between like Berglund-Hooch mirror symmetry, Batirov mirror symmetry, Artabani-Comparin-Gilbo mirror symmetry, Clark mirror symmetry. And there's a new result that my PhD student Emeric Malter is writing up right now that also does this in complete intersections. So he's able to show that Batirov-Borisov and Libgober and Teitelbaum, an example of mirror symmetry back in the 90s by Libgober and Teitelbaum, are also equivalent. So this is a really useful and hands-on technique once you've done the startup costs. So yeah, I'll stop here. Sorry for going over. Thank you so much for your time.